In 1964, one of the greatest minds in physics history stood before an audience at Cornell University and made an extraordinary confession. Richard Feynman, Nobel laureate, architect of quantum electrodynamics, a man who had helped build the atomic bomb and revolutionized our understanding of light and matter, looked directly at his audience. He said, "I think I can safely say that nobody understands quantum mechanics. Not some people struggle with quantum mechanics. Not quantum mechanics is difficult to grasp. No, nobody, including, by his own admission, himself." Now pause and consider what this actually means. Here was a physicist who had spent his entire adult life working with quantum mechanics. A man who could calculate the behavior of electrons to 11 decimal places of accuracy. A genius who had won the Nobel Prize for his contributions to the very field he was now claiming nobody understood. Was this false modesty? Was it a joke? Was Feynman simply being theatrical? Oh, no, too. He was being precise. And he was being honest. And once you understand why he was right, you will never look at reality the same way again. Because Feynman was not admitting ignorance. He was revealing something far more profound about the nature of understanding itself. He was telling us that the universe operates according to rules, that our human minds evolved to track tigers and find berries on an African savanna, are fundamentally incapable of picturing. And here's the beautiful irony. This admission of incomprehension is not a failure of physics. It is one of physics' greatest triumphs. To understand why Feynman's confession matters, we need to understand what understanding actually means in physics. And to do that, we need to travel back to a time when physics seemed to make perfect sense. For over 200 years, from Newton to the dawn of the 20th century, physics operated according to a principle that felt obvious and inevitable. If you want to understand how something behaves, you build a mental picture of it. You imagine billiard balls colliding. You visualize waves rippling across a pond. You picture planets orbiting the sun like clockwork mechanisms. This approach was spectacularly successful. Newton's mechanics could predict the motion of cannonballs and comets with equal precision. Maxwell's equations described electricity and magnetism as waves propagating through space. Everything had a shape, a position, a trajectory you could imagine in your mind's eye. Understanding, in this classical era, meant being able to picture what was happening. If you could imagine it, you could understand it. If you could understand it, you could predict it. Then came the 20th century, and everything fell apart. When physicists began probing the atom, they discovered something disturbing. The rules that govern the very small were nothing like the rules that governed the everyday world. Particles sometimes behaved like waves. Waves sometimes behaved like particles. Things seemed to exist in multiple places at once, until you looked at them. The act of observation itself seemed to change what was being observed. At first, physicists assumed this was a temporary confusion. Surely, with enough cleverness, someone would find a way to picture what was really happening. Someone would discover the hidden mechanism, the underlying clockwork, that made quantum mechanics make sense. That someone never came. Not because physicists were not clever enough, but because there is no underlying clockwork. There is no hidden picture. The universe, at its most fundamental level, simply does not work in a way that human imagination can visualize. This is what Feynman meant, and this is why he was right. Let us begin with the most famous experiment in all of quantum mechanics, the double-slit experiment. Richard Feynman himself called it the only mystery of quantum mechanics. Here's the setup. Imagine a wall with two narrow vertical slits cut into it. Behind the wall is a detection screen that records where particles land. Now, imagine firing tiny particles, say electrons, one at a time toward the wall. What would you expect to happen? If you are thinking classically, the answer seems obvious. Each electron must go through one slit or the other. Some electrons will go through the left slit and hit the screen behind it. Some will go through the right slit and hit the screen behind that. After firing many electrons, you should see two vertical bands on the detection screen. This is not what happens. What actually appears on the screen is an interference pattern, alternating bands of high and low electron density, exactly like what you would see if you had sent waves through the two slits instead of particles. Waves going through both slits at once, spreading out, overlapping, reinforcing in some places and canceling in others. But wait, we fired single electrons, one at a time. How can a single electron interfere with itself? How can something that is definitely just one particle somehow go through both slits simultaneously? Perhaps you might think the electrons are somehow bouncing off each other or interacting in some complex way. But no, we fired them one at a time. Each electron was completely alone when it passed through the apparatus. Well then, perhaps each electron really does go through just one slit, and we simply cannot predict which one. Perhaps the interference pattern emerges from some subtle statistical effect we do not yet understand. So physicists devised a clever test. They placed detectors at the slits to observe which path each electron took. Now they would know for certain, left slit or right slit. And here is where reality becomes impossible to picture. When they observed which slit the electrons went through, the interference pattern disappeared. The electrons suddenly behaved like ordinary particles, forming two simple bands behind the slits, exactly as classical intuition would predict. Stop. Radio. Think about that for a moment. The same electrons, the same apparatus, the same slits. But when you do not look at which path they take, they behave like waves, going through both slits at once, creating an interference pattern. When you do look, they behave like particles, going through one slit or the other, creating two simple bands. The act of observation changes what happens. Now, here is where most explanations go wrong. Most popular accounts of quantum mechanics at this point invoke some kind of mystical consciousness effect, as if the electrons somehow know when a human mind is watching. This is nonsense, and Feynman would have been the first to say so. What actually matters is not consciousness, but information. To observe which slit an electron goes through, you must interact with it in some way. You must bounce a photon off it, or disturb it with a detector. This interaction, however gentle, is enough to destroy the delicate quantum behavior that allows interference. But here is what we cannot escape. Before the observation, the electron is not secretly going through one slit or the other. It is not that we simply do not know which path it takes. The electron genuinely, mathematically, physically does not have a definite path. It exists in what physicists call a superposition, a combination of going through the left slit and going through the right slit simultaneously. This is not a metaphor. This is not a way of expressing our ignorance. This is what the mathematics says, and every experiment we have ever performed confirms it. And here is the crucial point. There is no way to picture this. There is no mental image you can form of a single object genuinely going through two different places at once. Your brain evolved to track solid objects moving through three-dimensional space. It has no neural architecture for visualizing superposition. This is what Feynman meant when he said nobody understands quantum mechanics. It is not that the mathematics is too hard. Feynman could do the mathematics in his sleep. It is that the mathematics describe something that human imagination cannot picture, as Feynman himself put it, when explaining this to students. Don't keep saying to yourself if you can possibly avoid it. But how can it be like that? Because you will get down a drain. You'll get down into a blind alley of which nobody has yet escaped. Nobody knows how it can be like that. Now you might be thinking, surely this is just a limitation of our current understanding. Surely someday, someone will figure out what is really happening. Surely there is some deeper level of reality where things make sense again. This is a natural assumption. It is also almost certainly wrong. The reason we can be confident about this is not philosophical speculation. It is experimental fact. Physicists have spent nearly a century designing ever more clever experiments to catch quantum mechanics being sensible, to find the hidden variables, to discover the underlying mechanism that makes the strangeness go away. Every single experiment has confirmed that the strangeness is real. Consider what is known as entanglement. Take two particles and prepare them in a special quantum state where their properties are correlated. Then separate them by any distance you like, across the room, across the planet, across the galaxy. Now, measure a property of one particle. The instant you do, the corresponding property of the other particle becomes definite, even though nothing has traveled between them. Not faster than light, because no information is transmitted. But still, somehow, the two particles remain connected in a way that classical physics cannot explain. Einstein famously hated this. He called it spooky action at a distance, and spent decades trying to prove that quantum mechanics must be incomplete, that there must be hidden variables, pre-existing properties that we simply could not see, which would explain the correlations without any actual connection between distant particles. In 1964, a physicist named John Bell devised a way to test this. He showed that if hidden variables existed, certain statistical correlations in experimental results would have to obey specific limits. Quantum mechanics, if it was truly as strange as it appeared, would violate those limits. The experiments have been performed, many times, with ever-increasing precision. Quantum mechanics violates Bell's limits. Einstein was wrong. There are no hidden variables. The strangeness is not our ignorance. The strangeness is reality. But here is where it gets even more interesting. The same quantum mechanics that seems so bizarre at the level of individual particles is the foundation of everything you see around you. Every atom in your body, every photon of light entering your eyes, every electrical impulse in the neurons that are processing these words right now. All of it runs on quantum mechanics. All of it depends on particles existing in superpositions, on wave functions collapsing, on the mathematics of probability amplitudes that no human being can visualize. And yet, somehow, the macroscopic world appears solid and definite. Your coffee cup does not seem to be in a superposition of sitting on your desk and being on the floor. The moon does not appear to be smeared across the sky. Why not? This is the puzzle of decoherence. When quantum systems interact with many other particles, as they inevitably do in any large object, the delicate quantum superpositions get smeared out, entangled with the environment in a way that makes them impossible to detect. The interference patterns that reveal quantum behavior become so incredibly finely structured that they are, for all practical purposes, invisible. The strangeness does not go away. It just becomes undetectable. This means you are, at this very moment, a quantum mechanical object. Your atoms are doing things that cannot be pictured. Your brain is at some level a quantum computer, though not in the science fiction sense. Every particle in your body is following rules that nobody truly understands. And here is the beautiful irony. This does not matter for most purposes. We can use quantum mechanics with extraordinary precision. We can build lasers and transistors and MRI machines and quantum computers. We can predict the results of experiments to more decimal places than any other theory in the history of science. We just cannot picture what is actually happening. Perhaps the most famous illustration of quantum strangeness is the thought experiment devised by Erwin Schrödinger in 1935, not to celebrate quantum mechanics, but to mock it. Imagine, Schrödinger said, a cat in a sealed box. Inside the box is a radioactive atom, a Geiger counter, and a vial of poison. The setup is arranged so that if the atom decays, the Geiger counter triggers a mechanism that breaks the vial and kills the cat. According to quantum mechanics, the radioactive atom exists in a superposition. It has both decayed and not decayed until something observes it. But if the atom is in a superposition, then the Geiger counter is in a superposition of having triggered and not having triggered. And the poison vial is in a superposition of being broken and unbroken. And the cat is in a superposition of being alive and dead. Schrödinger thought this was absurd. A cat cannot be both alive and dead. Therefore, he argued, quantum mechanics must be incomplete or incorrect. But here's the thing. Schrödinger was wrong about the absurdity, if not about the discomfort. Quantum mechanics really does say that the cat is in a superposition until something breaks the isolation of the box and allows information about the cat's state to leak out. The reason we never observe cats in superpositions is not that superpositions do not happen at the macroscopic scale. It is that macroscopic superpositions decohere almost instantaneously. The cat becomes entangled with air molecules, with photons, with the walls of the box, and the superposition becomes impossible to detect. The strangeness is still there. It is just hidden. Now, you might be thinking, what actually happens when we open the box? Does the cat suddenly become alive or dead at the moment of observation? Was it already alive or dead before we looked, and we simply did not know? Here is the uncomfortable truth. Quantum mechanics does not answer this question. The mathematics tells us how to calculate probabilities. It tells us what we will observe when we look. But it does not tell us what happens before the observation. It does not tell us what is really going on when nobody is watching. And this is not a gap in our knowledge that further research will fill. This is a feature of the theory itself. Quantum mechanics is fundamentally a theory about observations and probabilities. It is silent on the question of what exists between observations. Different physicists have different philosophical interpretations of this silence. Some believe that multiple universes branch off at every quantum event. Some believe that consciousness plays a fundamental role in collapsing possibilities into actualities. Some believe that the wave function is a real physical thing. Some believe it is merely a tool for calculating probabilities. Feynman's response to these debates was characteristic. Shut up and calculate. The philosophical questions, he argued, are less interesting than the practical work of using the theory to make predictions and build technologies. The universe does what it does regardless of our interpretations. But even Feynman acknowledged that the fundamental strangeness never goes away. You can learn to work with quantum mechanics. You can master its mathematics. You can apply it with extraordinary success. But you cannot picture what it describes. Let us try another thought experiment, one that Feynman himself loved to discuss. Imagine a single photon, a particle of light, heading toward a half-silvered mirror. This is a mirror that reflects exactly half the light that hits it and transmits the other half. A beam splitter. What happens to our single photon? Classically, you might expect that each photon either reflects or transmits, with a 50% probability of each. And if you put detectors on both paths, that is exactly what you see. Half the time the photon is detected on the reflected path, half the time on the transmitted path, never both. But now, here is the trick. Instead of putting detectors on the two paths, put mirrors that redirect both paths toward a single point. Then put a detector at that point. What do you see? If each photon took just one path, you would expect to detect photons half the time from each direction, with the overall detection probability being some combination of the two paths. Instead, you see interference. The two possible paths, the reflected path and the transmitted path, combine quantum mechanically. Depending on the precise arrangement of the mirrors, the photon might always arrive at the detector, or never arrive, or arrive with some intermediate probability. A single photon, one indivisible quantum of light, interferes with itself. It must, in some sense, have traveled both paths simultaneously. But wait. If you put detectors on both paths instead of mirrors, each photon is only ever detected on one path, never both. So did the photon travel one path or two? The answer depends on how you set up the experiment. Change the experiment, and you change the reality. Not just your knowledge of the reality itself. This is what defies understanding. This is what no mental picture can capture. Here is one more. Imagine a particle, say an electron, approaching a barrier it does not have enough energy to cross. Think of a ball rolling toward a hill. If the ball does not have enough energy to get over the hill, it rolls back down. It cannot magically appear on the other side. Quantum particles can. This is called quantum tunneling, and it is not a rare or exotic phenomenon. It is happening right now, inside the sun. The nuclear fusion that powers our star requires protons to get close enough to fuse despite their electrical repulsion. Classically, the temperatures in the sun's core are not nearly high enough for this to happen. The protons do not have enough energy to overcome the barrier, but quantum mechanics allows them to tunnel through. The protons, instead of being definite particles with definite positions, are smeared out in probability way. Those probability waves extend slightly through the barrier, allowing a small but non-zero chance of the proton appearing on the other side. Without quantum tunneling, the sun would not shine. Without the sun, you would not be reading these words. Now, here is the puzzle. How does the particle get through the barrier? What happens during the tunneling process? Where is the particle while it is inside the barrier? These questions have no good answers. The particle does not tunnel through in any classical sense, like a ball rolling through a tunnel. The barrier region is not traversed in any ordinary way. The particle simply has a probability of being on one side and a probability of being on the other, and sometimes it ends up on the other side. The mathematics describes this perfectly. The predictions match experiments with incredible precision. But there is no picture, no visualization, no mental model of what actually happened. Let us step back and ask, where did all this come from? How did physicists discover rules that nobody can understand? The story begins in the 1920s, when physicists were struggling to explain the behavior of atoms. Classical physics predicted that electrons orbiting a nucleus should radiate energy continuously and spiral into the nucleus within a fraction of a second. Atoms should not be stable. Matter should not exist. Obviously, matter does exist. So something was wrong with classical physics. A young Austrian physicist named Erwin Schrödinger proposed an equation that described electrons not as particles but as waves. These waves could only fit around the nucleus in certain specific patterns, like the vibrations of a guitar string, and these allowed patterns corresponded to the stable orbits that classical physics could not explain. The Schrödinger equation worked brilliantly. It predicted the spectra of atoms with stunning accuracy. It explained chemical bonding. It became the foundation of all modern chemistry and solid-state physics. But here is the thing. Nobody derived the Schrödinger equation from first principles. It was not a logical consequence of earlier physics. As Feynman himself said, where did we get that equation from? It's not possible to derive it from anything you know. It came out of the mind of Schrödinger. Schrödinger guessed it. He made an inspired, intuitive leap, and it turned out to describe nature correctly. And even Schrödinger did not fully understand what his equation meant. What his equation meant. He initially hoped that the wave function, the solution to his equation, represented a real physical wave, perhaps a smeared-out distribution of electric charge. He was wrong. The wave function turned out to be a probability amplitude, a mathematical tool for calculating the likelihood of different observations. It is complex-valued, meaning it involves the square root of -1, and its square gives probabilities. What is the wave function, really? Is it a real thing in the world, or just a mathematical convenience? Physicists still argue about this nearly a century later. So here we are. Quantum mechanics is the most successful theory in the history of science. It underlies all of modern technology. It describes the behavior of atoms and light and matter with incredible precision, and nobody understands it. How should we feel about this? Feynman characteristically found it liberating. In one of his most famous lectures, he described the experience of learning quantum mechanics. If you will simply admit that maybe nature does behave like this, you will find her a delightful, entrancing thing. The trick, he said, is to stop demanding that nature makes sense on human terms. Stop asking how can it be like that, and start simply watching what happens. This is not anti-intellectual resignation. It is intellectual humility. It is recognizing that the universe is not obligated to be comprehensible to brains that evolved for very different purposes. Consider this. Why would you expect to understand the fundamental nature of reality? Your brain developed to help your ancestors survive on the African savanna. It is optimized for tracking objects at human scales, predicting the behavior of animals and other humans, finding food and avoiding predators. It has no reason, from an evolutionary perspective, to accurately picture the quantum behavior of subatomic particles. In fact, it is remarkable that we can understand as much as we do. The mathematical structures that describe quantum mechanics are not part of everyday experience. Yet human minds can learn to work with them, can make predictions, can test those predictions against experiment, can build technologies that exploit quantum effect. We cannot picture quantum mechanics, but we can calculate it. We can use it. We can even, in some abstract mathematical sense, know it. Perhaps this is what understanding actually means in physics. Not having a mental picture, but having a mathematical description that makes accurate predictions. Perhaps our demand for visualizable explanations is simply a human limitation, not a requirement of truth. Feynman once said, "To those who do not know mathematics, it is difficult to get across a real feeling as to the beauty, the deepest beauty, of nature. If you want to learn about nature, to appreciate nature, it is necessary to understand the language that she speaks in." Nature speaks in mathematics. Additionally, quantum mechanics is written in mathematics, and the mathematics is precise, beautiful, and successful beyond any reasonable expectation. We just cannot translate it into pictures. Let us step back and consider what we have learned. At the most fundamental level of reality, particles do not behave like tiny billiard balls. They do not have definite positions until they are observed. They can be in multiple states simultaneously. Now, they can be entangled with other particles across arbitrary distances. They can tunnel through barriers they do not have the energy to cross. None of this can be pictured. None of this fits into the categories our brains evolved to use. And yet, somehow, this strange quantum world gives rise to the solid, definite, comprehensible macroscopic world we live in. Atoms made of quantum particles combine to form molecules. Molecules form cells. Cells form brains. And those brains, running on quantum mechanics that they cannot picture, somehow figure out the rules that govern their own components. There is something almost miraculous about this. The universe has arranged itself in such a way that quantum strangeness is, for the most part, invisible at human scales. We get to live in a world of solid objects and definite outcomes, even though the underlying reality is nothing of the kind. And yet, when we look closely enough, when we build sensitive enough experiments, the strangeness peeks through. The double-slit pattern appears. Entanglement is confirmed. Quantum computers begin to harness superposition for computation. We are living at a moment in history when humans are learning to manipulate quantum effects directly. Quantum computers, quantum cryptography, quantum sensing. These technologies exploit the very features of quantum mechanics that nobody understands. We cannot picture what a qubit is doing when it is in superposition, but we can make it do useful work. This is perhaps the strangest thing of all. We can use what we cannot understand. We can harness what we cannot visualize. The universe obeys mathematical rules, and we can discover those rules and exploit them, even when the rules describe a reality that our minds were never designed to grasp. Richard Feynman was not a philosopher. He was famously skeptical of philosophy, often dismissing it as meaningless word games. But in his honest admission that nobody understands quantum mechanics, he made one of the most profound philosophical points in the history of science. Understanding, he was saying, is not one thing. There are different levels of understanding, different kinds of knowing. You can understand how to calculate something without being able to picture it. You can know the rules without comprehending what they mean. You can work with a reality that your mind cannot contain. And this is not a failure. This is progress. Before quantum mechanics, physicists assumed that any successful theory would be visualizable. If you could not picture what the equations described, the equations must be wrong or incomplete. Quantum mechanics shattered that assumption. The equations were right. The pictures were impossible. This was humanity growing up. This was our species confronting the fact that the universe is not made for us, does not operate according to our intuitions, and does not owe us comprehensibility. And yet here is the wonder. We figured it out anyway. Through mathematics, through experiment, through sheer stubborn persistence, we discovered the rules that govern the quantum world. We cannot visualize those rules, but we know them. We use them. We have expanded the boundaries of human knowledge beyond the boundaries of human imagination. Feynman once said that physics is like sex. Sure, it may give some practical results, but that's not why we do it. He did physics because it was beautiful. Because the process of understanding, even partial understanding, even understanding that you cannot quite picture, is one of the deepest joys available to the human mind. Quantum mechanics may be impossible to visualize, but it is not impossible to appreciate. The mathematical structures are elegant. The experimental confirmations are stunning. The technological applications are revolutionary. And the sheer strangeness of it all, the fact that reality is so much stranger than anything we could have imagined, is itself a source of wonder. When Feynman said that nobody understands quantum mechanics, he was not expressing despair. He was expressing awe. The universe is strange beyond our capacity to picture, and we have learned to work with that strangeness anyway. What could be more wonderful than that? The invitation, then, is not to feel frustrated by the limits of human understanding. It is to feel amazed by how far we have come despite those limits. It is to approach the quantum world with humility and curiosity, not demanding that it makes sense on our terms, but accepting it on its own. As Feynman said, if you will simply admit that maybe nature does behave like this, you will find her a delightful, entrancing thing. Nature is quantum. Nature is strange. Nature is beautiful beyond our capacity to picture, and the adventure of discovering more is only beginning. Entangled, closing, visual.